So we've looked at a few differentiation rules. We've seen the power rule, product rule, and quotient rule. This is going to be a new rule, which is called the chain rule. And the chain rule deals with finding the derivatives of composite functions, so functions within functions. So first thing I want to do is actually write out what the formula is going to be. So the chain rule says I need to differentiate a function within a function, which is a composite function, or you can also call that the composition of functions. So when I'm differentiating, I have these different layers here. Notice I have g of x being plugged inside f of x. So my outside layer would be f, the inside layer is g. When I deal with the layers, I have to deal with the outside layer before I can get to the inside. So my formula for the derivative would be the derivative of the outside, keeping the inside intact, because all I'm dealing with is the outside layer right now. Then I go back and I multiply by the derivative of the inside. So I have f prime of g of x times g prime of x. In words, that is the derivative of the outside layer. But once I differentiate the outside layer, I haven't done anything to the inside yet, so I'm going to keep the inside exactly the same. And then I go back and I multiply by the derivative of the inside. And you're going to keep that all on one line, so it's all being just multiplied together. So like I said, differentiate the outside layer, keeping the inside layer, then go back and multiply by the derivative of the inside. So let's look at an example. So our first example, we're going to look at a pretty basic one. We have y is equal to x squared plus 1 all raised to the third power. And I want to take the derivative of this. Now in the past, if I wanted to differentiate this, I could either expand this out and use product rule, or completely expand it and multiply out the entire way, and then use power rule term by term. But chain rule kind of allows us to have a shortcut with that. So I'm going to go on this side. I'm actually going to list off my layers here so we can actually see what's on the outside, what's on the inside. And once I do that, it's a little bit easier to distinguish how am I actually going to take the derivative from there. So if I call layer 1 the outside layer, this is the thing that applies to everything in the problem. This would have to be the power of 3. Once I take away the power of 3, I'm left with the inside layer, which is at x squared plus 1. So when I differentiate, I'm going to differentiate the outside layer first. So if I'm dealing with that power of 3, that's just a normal power rule. I'm going to take the 3, pull it out in front, subtract 1 from the exponent. So I have 3 out in front, subtract 1 from the exponent. So now it's to the power of 2. But all I've done is deal with the outside layer. So the inside is going to stay exactly the same, x squared plus 1. Then I go back and I multiply by the derivative of the inside, which would be the derivative of this x squared plus 1, which goes to 2x. So if I'm looking at the layers here, this was the derivative of layer 1, which is the outside layer. This was the derivative of layer 2, which is the inside layer. Now, if I wanted to simplify this, the only thing I would do would be multiply the 3 and the 2x together to make 6x in front, with the x squared plus 1 quantity squared behind it. But a lot of times we're told we do not have to simplify things, and so we can leave our answer just like that. But if we're required to simplify, or if we're trying to make it match a multiple choice answer, this is where we would go with the end of the problem. So let's look at another one, kind of similar to that, just different example. So let's say I'm given y is equal to the 5th root of x to the 4th minus 3x plus 9. And that's all underneath the root. So again, I'm going to go ahead and list off my layers. So if I think about what the outside layer is, the outside layer would be that 5th root. Now, I'm going to have to differentiate that using power rule, so I'm going to go ahead and rewrite that as parentheses to the 1/5. So the radical has an exponent of 1/5. And then once I take away that layer, I'm left with the x to the 4th minus 3x plus 9 layer, which is my inside layer. So once I differentiate, I take the derivative of the outside, which is at 1/5 power, so I can bring the 1/5 in front, keep the inside, subtract 1 from the exponent. Well, if I'm subtracting 1 from 1/5, 1/5 minus 1 is negative 4/5. Now, like I said, I'm going to keep the inside because all I've done is deal with the outside layer. Then I go back and I multiply by the derivative of the inside. So the derivative of this x to the 4th minus 3x plus 9 would go to 4x cubed minus 3x. Now occasionally we're going to have some problems that look a little bit more complex. Sometimes we can avoid that, sometimes we cannot. So here's what I mean by that. Let's say I'm given f of x is equal to the cubed root of x squared minus 1 quantity squared inside the cubed root. Well, if I try to break apart the layers, just jumping straight into it, it looks like I actually have 3 different layers, which I do. The outside layer, which applies to the entire function, would be the cubed root, which is the 1/3 power. After that, if I take away the cubed root, the next layer would be the power of 2, so the squared. And then if I take away that, the inside layer would be x squared minus 1. It is possible to use chain rule with 3 layers. We'll see that in a moment. However, if I can avoid chain rule with 3 layers, I definitely want to do so. So go back to the beginning and realize if this is being raised to a power and it's all inside a root, I can actually combine these exponents together into a rational number, which is actually going to simplify my work here. So here's what I mean. All I'm doing right now is going to rewrite this. So I'm keeping the x squared minus 1. If I rewrite it as power over root, this is raised to the 2/3 power. That's not taking a derivative yet, that's just rewriting it. This now only involves 2 different layers. My outside layer would be the power of 2/3, and then my inside layer would be the x squared minus 1. Given the choice between 2 layers or 3 layers, I always want to pick the option that gives me the least amount of work, which of course would be 2 layers, not 3 layers. So I'm going to deal with the 2 layers instead of looking at the 3 layers. So if I deal with the 2 layers, f prime of x says take the derivative of the outside layer first. So I'm bringing down the exponent of 2/3, but I'm going to keep the inside layer intact, so I'm keeping that x squared minus 1. Then I need to subtract 1 from the exponent, so 2/3 minus 1 is negative 1/3. And then I'm going to go back and multiply by the derivative of the inside, which would be 2x. And so there's my chain rule for my derivative here. Now we can also see these types of problems with trig functions. So I'm going to start with a basic one. Let's say y was equal to cosine of 4x. If we do not see parentheses in the problem, a lot of times you can look at it and really help yourself by trying to figure out where would the implied parentheses be. In this case, all of 4x is inside the cosine, so I'm actually going to draw the parentheses around the 4x just to help me see the layers a little bit better. So when I go through and write out my layers here, the outside layer would be the cosine, so that's layer 1. And then the inside layer would be the 4x. So the derivative of cosine goes to negative sine, keeping the inside of 4x, times the derivative of 4x, which is the inside layer, and that just goes to 4. And I could rewrite it just to clean it up a little bit by putting that 4 in front, but it doesn't change our answer, of course. This is a little bit trickier, though, when the trig function has an exponent attached to it. So let's say I'm given y is equal to sine squared of 2x cubed plus 4. Well, in this case, I have a lot of different things happening with this problem. I need to first recognize that the power of 2 is applied to the entire function because all of sine is being squared here. And then this 2x cubed plus 4 is inside the sine. So often when you see this type of problem, I would highly recommend rewriting it first by writing it as sine of 2x cubed plus 4, all being squared because that power of 2 applies to, like I said, all of the sine. Then it's clear to see what your layers are actually going to be. So my outside layer in this case would be the power of 2. There's a middle layer of the sine, and once I take those away, then I'm left with the inside, which is 2x cubed plus 4. Unlike one of our previous problems, there is no way to avoid the 3 layers in this case. I just have to take it step by step with the chain rule, and just start with the outside, work my way towards the inside. You always start with the outside layer, work your way into the inside. So with y prime, I have the derivative of the outside. Well, the outside layer for everything is that power of 2. So I'm going to pull down the power of 2 in front, keep all of the inside the same, subtract 1 from the exponent. So technically that's to the power of 1, but we never actually really write that. It's just going to be implied. And then, like I said, I'm keeping all of the inside the same. So I'm keeping that sine of 2x cubed plus 4 all the same on the inside. Then I can go back and multiply by the derivative of layer 2, which is the middle layer, the sine of the parentheses. Derivative of sine is cosine. Again, keeping the inside intact. I haven't actually gotten to the very inside yet. Then I'm going to go back and multiply by the derivative of the third layer, which would be that 2x cubed plus 4. The derivative of 2x cubed plus 4 goes to 6x squared. So if I label this for you, this was taking the derivative of the outside, which is layer 1. This was differentiating the middle layer, which is layer 2. And this was differentiating layer 3, which is the inside. And all of that's being multiplied together. And of course we could simplify that, but my purpose is just showing you how to actually use the chain rule to find the derivative here. So the last example deals with when we have our exponents, it really matters where the exponent is in terms of our trig function. So let's say that I have y is equal to tangent of x squared. Well, in that case, I need to ask myself, what is actually being squared? Because that'll help define what my layers are going to be. Well, in this case, notice the power of 2 is only attached to the x. And so only x is being squared. It has nothing to do with the tangent. So my implied parentheses, if I were to draw those in, would be around the x squared. So all of x squared is on the inside of tangent, which means I have two different layers here. So chain rule definitely does apply since I have the layers. The outside layer would be the tangent. The inside layer would be the x squared. So this is a pretty basic chain rule once you recognize that. So y prime, I differentiate tangent, which goes to secant squared, keeping the inside intact, times the derivative of the inside, which is the derivative of x squared, and that of course goes to 2x. Now I could slightly change this problem, and by changing it, it actually changes the strategy. So here's what I mean. Let's say I go back to that original problem, ignoring the red parentheses, where I had y is equal to tangent of x squared, but instead of x squared, I write it as tangent squared x. They look pretty similar, but they're completely different. So in this case, again, if I ask myself what is being squared here, I have to notice that the power of 2 is attached to the tangent, so all of tangent x is being squared. This is very similar to one of our previous problems. I highly recommend you go ahead and rewrite this as tangent x in parentheses raised to the power of 2, because then you can clearly see the outside layer would be the power of 2, the inside layer would be the tangent. So layer 1, outside layer, is the power of 2, inside layer is that tangent x, which makes it very different than the previous problem on the same page. So if I differentiate, chain rule says take the derivative of the outside, that's the power of 2, so I'm going to bring down the 2 in front, keep the inside the same, subtract 1 from the exponent, so technically there's a power of 1 right here, but again, we don't write that. So I'm keeping the inside tangent x the same. Then I'm going to go back and multiply by the derivative of the inside. Well, the derivative of tangent is secant squared x. And of course, this answer is very different from that answer because we're dealing with two different types of functions, and where the exponent was completely changes what the problem is supposed to look like. So when you're solving these types of problems and you're trying to differentiate, be very careful about looking at where the exponent is or where the parentheses are, and ask yourself, okay, what's actually getting the exponent, what's being applied here, what would be on the inside, what would be the outside. If it helps write out your layers, then you can differentiate using the chain rule a bit easier, and hopefully that'll help you when you get stuck on different types of problems.